This is SpaceTime Series 27, Episode 154, for broadcast on the 23rd of December 2024. Coming up on SpaceTime, new studies showing the moon's actually a lot older than we thought. NASA's Perseverance Rover finally crests the top of Jezero Crater's rim. And understanding the tectonic mystery behind South Australia's strange pink beach sands. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
New researchers discovered that the Earth's moon may be an awful lot older than we thought. Scientists found evidence suggesting that the moon's crust underwent extensive remelting around 4.35 billion years ago, and that would have masked a far older history. The moon's thought to have been formed when a Mars-sized planet, which scientists have named Theia, collided with the early proto-Earth around 4.5 billion years ago. The colossal impact turned both bodies into a magma ocean of melted rocks, which eventually coalesced and solidified to form the Earth. However, some of the ejected debris from that impact was thrown up into orbit around the Earth, and it gradually accreted and solidified to form the Moon. However, this new research argues that there was a period well after that when the Moon's surface was melted again and changed the appearance of certain rock samples that made them look younger than what they really were. Now, if this evidence is accurate, it means the Earth's moon's actually around 4.53 billion years old. It's all very confusing. Previous attempts to uncover the moon's true age have yielded estimates that lie several hundred million years apart. While some researchers suggest that our cosmic companion was formed 4.35 billion years ago, others date the birth at 4.51 and now 4.53. One of the most striking inconsistencies is of a stony nature. You see, almost all the lunar rock samples we have here on Earth point to the younger age. In the millions of years that followed the giant impact, the newly formed moon cooled and moved further and further away from the Earth until it reached its current orbit at a distance of around 384,400 kilometres. It's still moving away from the Earth today at a couple of centimetres every year. The study's lead author, Francis Nemo from the University of California, Santa Cruz, says his team were especially interested in the phase when the distance between the Earth and the Moon was just a third of today's distance. Now, at that time, there were various differences in the position and shape of the Moon's orbit. Now, among other things, it became far more elliptical, so that the orbital speed of the Moon at its distance from the Earth varied considerably within each orbit. And the thing is, that would have generated an awful lot of gravitational tidal heating, partially melting the lunar interior. Now, all this is similar to what we see today with Jupiter's moon Io, which travels around the gas giant in a slightly elliptical orbit. The enormous tidal forces of Jupiter, together with that of Io's other companion moons, causes the moon to be constantly stretched and squeezed, generating friction and consequently heat. And all that makes Io the most volcanically active body in the solar system. And based on this new study, Earth's moon went through a similar phase. Nemo and colleagues' calculations suggested the heat flow from the lunar interior was sufficient to melt and churn through the entire mantle. Now, while a magma ocean never covered the entire lunar surface, over the course of several million years, the heat from the interior gradually reached pretty well every part of the surface, liquefying most of the crust, possibly several times over. Now, the authors say that in some places the hot lava penetrated right through to the surface. In others, magma was injected beneath the surface, heating the rocks around it. And this volcanic history is decisive for determining the age of crustal rocks. Now, when they form, rocks, including those on the Moon, contain various radioactive isotopes. Isotopes are variations of certain atoms that differ in the number of neutrons they have in their nucleus. Now, as long as the rock's hot, it can exchange isotopes with its surroundings. But as it cools, those isotopes become locked in, and the composition becomes set. Then the trapped isotopes begin to radioactively decay, and so the geological clock starts ticking. Lunar rock samples, therefore, don't reveal their original age, but only the age when they were last strongly heated. However, there are some unique crystals in rocks known as zircons that are extremely tough and heat resistant, and uranium atoms trapped inside these crystals decay into lead atoms at a set rate. So, by comparing the ratio of uranium to lead inside zircon crystals, astronomers can determine the exact age when the zircon crystals were first formed. And they're showing a more distant, earlier history than other crustal rocks, and so are telling a different story. The violent volcanism shaped the moon's crust around 4.35 billion years ago. But the zircons are much older, at 4.53 billion years. And the story doesn't end there. These new findings are also resolving many other contradictions that had previously puzzled astronomers. For example, the comparatively few craters on the moon argues against its old age. In such a long time, astronomers think our cosmic neighbour should have witnessed more impacts. Lunar volcanism now offers an explanation. Lava from the moon's interior would have filled the early impact craters and thus made them unrecognisable. The composition of the lunar mantle also posed a problem. This is the layer of rock that lies directly beneath the moon's crust, and its composition differs from that of the Earth in several key aspects. However, if the moon's interior melted a second time round, as this new study would indicate, some substances could have sunk from the mantle down to the iron core below, and that would explain the compositional differences between the moon's mantle and parts of the Earth. The new results mean that all the pieces of the puzzle that previously didn't fit together are now forming a coherent overall picture of our lunar partner's formation. It puts a full stop at the end of the story. This is SpaceTime. Still to come, NASA's Perseverance Rover finally crests the top of Jezero Crater's rim, and planetary plate tectonics are solving the mystery of South Australia's strange pink beach sands. All that and more still to come on SpaceTime. There are celebrations at JPL today, with NASA's Mars Perseverance Rover finally cresting the very top of Jezero Crater's rim. And mission managers say the road ahead will be even more scientifically intriguing. And the good news is it'll probably be somewhat easier going now that the six-wheeled car-sized mobile laboratory has completed its long climb to the top. Perseverance crested the top of Jezero's rim at a location known as Lookout Hill, and it's now rolling towards what will be its first new science stop following its month-long climb. The rover made the ascent in order to explore a region of Mars unlike anywhere it had investigated before. Taking about 3.5 months and ascending over 0.5 kilometre in elevation, the rover climbed 20-degree grades, often in slippery, sandy conditions, making stops along the way for scientific observations. Since landing in Jezero Crater back in February 2021, the Mars Perseverance Rover has completed 4 science campaigns. There was the crater floor, then the fan front, the fan being the build-up of river delta sediment, then the upper fan, and finally the margin unit. The science team are calling what will be Perseverance's 5th scientific campaign the Northern Rim. That's because the route will cover the northern part of the southwestern section of Jezero's rim. Perseverance's Deputy Project Manager Stephen Lee from NASA's Jet Propulsion Laboratory in Pasadena, California, says that over the first year of the Northern Rim campaign, the rover is expected to visit 4 sites of geological interest, take several samples, and drive about 6.4 kilometres. The Northern Rim campaign brings completely new scientific riches as Perseverance roves into fundamentally new geology. That's because it marks the transition from rocks that were partially filled in Jezero Crater when it was formed by a massive impact about 3.9 billion years ago to the rocks from deep inside Mars that were ejected upwards from the crater rim as a result of that impact. Scientists believe that these new rocks will represent pieces of the early Martian crust, and therefore will be among the oldest rocks found anywhere in the solar system. Investigating them could help science understand what Mars, and for that matter the Earth, may have looked like just after the solar system formed and planets began to solidify 4.6 billion years ago. With Lookout Hill now in its rear-view mirror, Perseverance is headed for a scientifically significant rock outcrop about 450 metres down the other side of the rim, known as Witch Hazel Hill. Witch Hazel Hill represents over 100 metres of layered outcrop, where each layer is like a page in a Martian geological history book. So as Perseverance drives down the hill, it's sort of going back in time, investigating the ancient environments of Mars recorded in the crater rim. Then, after a steep descent, Perseverance will turn its wheels away from the crater rim and head towards Lac de Chimay, about 3 kilometres further south. Lac de Chimay intrigues scientists because, being located on the plains beyond the rim, it's far less likely to have been significantly affected by the formation of Jezero Crater. After leaving Lac de Chimay, the rover will traverse about 1.6 kilometres back to the rim in order to investigate a stunning outcrop of large blocks known as megabreccia. These blocks may represent ancient bedrock broken up during the Ascent impact, a planet-altering event that likely excavated deep into the Martian crust as it created an impact basin some 1,200 kilometres wide 3.9 billion years ago. Needless to say, it means interesting times ahead. This is SpaceTime. Still to come, the mystery of South Australia's strange pink sands, and later in the science report, a new study shows that guys tend to head to the bar faster when the women are scarce. All that and more still to come on SpaceTime. Deposits of strange deep pink sand washing up on South Australian beaches is shedding new light on when the Australian tectonic plate began to subduct beneath the Pacific plate. And the findings, reported in the journal Communications, Earth and Environment, are also exposing the existence of a previously unknown ancient Antarctic mountain range. The pink sands are composed of a mineral called garnet. Now, garnets known to have formed locally during the Delamerian orogeny, an event which created the Adelaide Fold Belt around 514 to 490 million years ago, and also during the formation of the Jezero Crater in western South Australia between 3.3 and 1.4 billion years ago. The problem is these ages don't match up with the garnet sands now being found on South Australian seashores. One of the study's authors, Charmaine Verhat from the University of Adelaide, says new dating shows that the garnet grains are around 590 million years old. That's too young to have come from the Jezero Crater and far too old to have come from the eroding Adelaide Fold Belt. The authors were able to establish the new date using a new lutetium-hafnium laser mass spectrometer technique. Garnet requires high temperatures to form and is usually associated with the formation of large mountain belts. But the 590 million year old age window was a time when the South Australian crust was comparatively cool and non-mountainous. And Verhat and colleagues were able to establish that this garnet didn't originate from local source rocks. The thing is, it must have originated nearby because garnet is typically destroyed through prolonged exposure to marine environments. Now, the authors have discovered that the glacial sedimentary deposits of the Cape Jervis Formation, outcropping along the South Australian shorelines, contains layers of sand which also contain garnet that's also around 590 million years old. And ice flow indicators in these glacial sedimentary deposits suggest that the garnet-rich glacial sands were brought to Australia by a northwesterly moving ice sheet during the late Paleozoic Ice Age, when Australia and Antarctica were attached as part of the supercontinent Gondwana. And here's where it gets really interesting. Garnet dating back to the same period has also been found in an outcrop in the Transantarctic Mountains in East Antarctica, right at the edge of a colossal area completely concealed by a thick ice sheet. And researchers believe that this area contains evidence for a 590 million year old mountain belt hiding below the Antarctic ice. Now, while it's not currently possible to sample directly under this ice sheet, it's conceivable that millions of years of ice transport eroded the bedrock underneath and transported this garnet northwestwards towards the conjugate Antarctic Australian margin. The garnet deposits were then locally stored in glacial sedimentary deposits along the southern Australian margin until fresh erosion liberated them and waves and tides concentrated them on South Australian beaches. So, these findings are suggesting the discovery of a major mountain building event that redefines the timing of the onset of convergence in the Pacific Ocean. Verhat says it's fascinating to think scientists were able to trace tiny grains of sand on a beach in Australia to a previously undiscovered mountain range buried deep below the Antarctic ice.
Usually if we see pink beach sands that contain a lot of garnets, the garnets must have been eroded from somewhere. That could be if there's like a mountain belt close by. For example, if you would go to the Himalayas and you would walk through the Himalayan foreland basin and you'd be walking along the rivers and the beaches, you might find a lot of garnets in there because they usually occur in highly metamorphic mountain ranges, such as the Himalayas. So in the case of South Australia, when we were walking along the beaches and we saw that the beaches contain a lot of those pink garnets, we were just wondering where could they be coming from, because we don't really have a big existing mountain range nearby here in South Australia. We do have the Adelaide Fault Belt, which contains garnet, and it has some form of topography, but it isn't really a big, impressive mountain range or anything. And there isn't a large volume of garnet in the Adelaide Fault Belt, not large enough for it to erode that many garnets along all of the beaches around South Australia. So we were like, how can we try to solve this problem? And at the time when we found those pink garnets on the beach, we actually were developing a new dating method that we could apply to garnets as well. So at the time when we found those garnets, we were like, why don't we just try to analyze those garnets and see what age we get from them? Because that's the easiest way to match certain garnets to certain basement rocks. Once we got our ages back from our laser session, we realized that just gave us another question, because the ages we got from those garnets didn't line up with anything. So they were too young to be from the Adelaide Jezero Crater, and then they were too old to come from the fault belt. So we were wondering what could be another source for those garnets. And the only possible option close by was the Permian glacial sediments that are also cropping out along South Australia, which we found out also contain a lot of garnets. So we decided to sample those glacial sands as well. So we scooped some sands from the glacial sands, which had a lot of garnets in them, and we tried to analyze those as well. And then when we got our results back, we realized that the garnets from the glacial sands had the same age as the garnets on the beach. So we found our match.
And where would they have come from?
That's the problem with glacial sediments. So we know that glacial sediments, if there's indicators that they were deposited by large ice sheets, we know that they aren't originally from this location. So a big, massive ice sheet must have brought them to South Australia during the glaciation of that ice sheet. So the glaciation we're talking about is the late Paleozoic Ice Age, which occurred around the Permian Carboniferous time zones. So at that time, looking at all plate tectonic reconstructions, we know that South Australia was connected to East Antarctica back in the days. So if we're thinking about ice sheet movement, we can look at the sands and you can look at the pebbles and see what the lithologies of these pebbles are. So are they sandstone? Are they metamorphic rocks? Where could they be coming from? And then those pebbles, they can have marks in them, gather marks or troughs, and that can indicate what way the ice sheet was flowing. So in this case, we found out that through other researchers who had been studying this before us, they concluded that the ice sheet must have come from a source somewhere southeast to us. So if you would look back at the plate tectonic reconstructions and you would go southeast from the Adelaide area, you would end up in East Antarctica.
Wow. That sort of puts the cherry on the cake, doesn't it?
Yeah.
It's a detective story, isn't it?
It is. It kind of is. And we didn't expect to find an outcome as exciting as this one, because once we figured out that they might have been coming from East Antarctica, we're pretty certain they are, we realized that there isn't really anything of the same age. So we're talking about an age around 590 million years ago, which is in the Ediacaran time period. We don't really find any mountains or outcrops in East Antarctica with that age, because obviously East Antarctica is covered by a large ice sheet, and most of the geology in East Antarctica is hidden beneath that ice sheet. And based on, I think there was one small outcrop in the Transantarctic Mountains where they got a similar age for the garnet, but it's so far away, so we assume or we suspect that there might be a large geological province underneath the ice sheet, an old ancient mountain belt that was eroded by the ice sheet in the late Paleozoic Ice Age that we now find back in South Australia, but it's now hidden in the ice, underneath the ice in East Antarctica, and we don't know if you'd ever be able to drill into it or find it if it wasn't for this study.
Garnets, when the average person thinks of garnets, they think of a gemstone, something pretty to put in a ring or on a necklace. Tell me about garnets. How are they made?
Yeah, so garnets are in fact really pretty minerals. So you often find them in color red or pink, and they're translucent. So if you find a very clear mineral that doesn't really have inclusions, it's really nice to put them in jewelry, as you just said. So garnet is a metamorphic mineral, which means that it grows when deep in the Earth's crust, you've got very high temperatures and pressures pushing all the rocks together. And because of this heat and this pressure, your rocks will start melting and they will start forming another rock. So in this case, for garnets, it's usually when you have old mudstones or sedimentary rocks that get buried very deep into the crust of the earth, and you have an ongoing mountain building process, which is pushing everything together. So you've got two continents trying to mix each other. That's when you start forming garnets. So you need pressure and temperature conditions that are high enough for garnet to form. And then after some time, when the garnet has been sitting in the rock, it'll start getting eroded. So when everything or all the rocks above the unit with the garnets is eroded away, that's when you will see garnet at the Earth's surface, which isn't very common.
That's Charmaine Verhart from the University of Adelaide, and this is SpaceTime. And time now to take a brief look at some of the other stories making news in science this week with a science report. A new study has shown that ambulance and taxi drivers have the lowest levels of death due to Alzheimer's disease compared to other occupations. The findings, reported in the British Medical Journal, suggest that frequent spatial processing tasks might offer some protection against the illness. Scientists analysed death certificates for 443 different occupations between 2020 and 2023, including cause of death, usual occupation, and socio-demographic information. After adjusting for age and socio-demographic factors, the authors found that taxi drivers and ambulance drivers have the lowest proportion of deaths from Alzheimer's of all occupations examined, and also when compared with the general population. But interestingly, the authors noted that this trend wasn't seen in other transport-related jobs, such as bus drivers or aircraft pilots, possibly due to their reliance on predetermined routes. ANSTO's Opal nuclear research reactor at Lucas Heights in Sydney's southern suburbs has officially powered back on and recommenced general operations. It follows a several months-long planned shutdown to carry out essential maintenance and upgrades. Central to these upgrades was the replacement of Opal's cold neutron source, located next to the reactor's core. The 3-metre-tall device slows down neutrons as they travel from the Opal reactor through to the large scientific neutron beam instruments, allowing researchers to look at the structure of materials in atomic detail. The planned shutdown also enabled extensive software and hardware upgrades to Opal's first reactor protection system, a digital system that monitors the reactor's crucial parameters. The system is the first line of defence for Opal to automatically shut down safely if the parameters are exceeded. As Australia's only operational nuclear reactor, Opal produces neutrons that form the radioisotopes required for nuclear medicines, and they're used to diagnose a range of medical conditions and cancers. Opal also supplies more than half of the world's demand for irradiated silicon. That's used in electronics and green technologies. Now here's something that may not come as a surprise. A new study has found that guys tend to head to the bar faster when women are scarce. The findings, reported in the journal Biological Letters, shows that if you're out at the pub with a group of mates, which include both males and females, then the men will be quicker to head to the bar and buy drinks if they outnumber the women in your group. The authors monitored 163 mixed-sex groups out for drinks at 3 taverns in the Boston area over a period of 7 nights. Good work if you can get it. They found that when males outnumbered females in the group, the alpha male would take less time to stride up to the bar, make physical contact with it, and offer to pay for the first round of drinks. The researchers say that the findings suggest that, just like other animals, male humans tend to invest more resources when the competition for a mate is higher. A recent study has been looking at the fascinating case of people who suffer from aphantasia, a characteristic some people have related to how their mind and imagination work. Having aphantasia means you either don't have or have a reduced level of visual imagination, keeping you from picturing things in your mind. The research by the University of Sussex found that 0.8% of the population is unable to form visual mental images, and 3.9% of the population were either unable to form mental images or had only a very dim or vague mental imagery. Tim Mendham from Australian Skeptics says it's like asking someone not to think of a pink elephant. Well, of course, that's the first thing, in fact the only thing you think of. That is, unless you suffer from aphantasia.
The pink pink elephant test is basically the old story of that if I say, don't think of a pink elephant, you instantly do think of a pink elephant, which is pretty normal. Actually, don't think of a rhinoceros, please, and you do think of a rhinoceros, or anything else for that matter. So people sort of immediately call up a visual memory and they respond in kind. It's very hard to stop doing that, except for people, apparently, who have a thing called aphantasia, who apparently cannot visualize things. They cannot call up a visual image, a memory, or whatever of something just because it's not in their brain to do so, which is interesting. This is basically the whole spectrum idea. There's everything that affects humans. You run from people with very strong visual imagery skills or proclivities down to someone who has no visual proclivity at all. Certainly not just looking at something, but actually remembering something or calling it up in their head. So aphantasia is this condition. It's like if you're reading a book and you have normal visual imagery skills, you can sort of see a character doing something. You have a picture of someone. If you have aphantasia, you can't visualize something. So basically, it just happens.
It's very difficult to survive.
Well, they survive often quite well, just as good as anybody else. Half the time, they would not know they can't do this because they don't know what they can't do until they gradually realize that other people are calling up an image in their head. It's not looking at something. You can still cross the road, but it's actually calling up an image in your head. Sometimes these people have better audio memory. They can call up a sound. Someone says a trumpet, so they're hearing beep, 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 whereas someone with a visual thing might be seeing a trumpet in their head. So it's a bit of swings and roundabouts. And they're also suggesting that some people perhaps, and this is very much perhaps, people with aphantasia or aphantasics, as they call them, might be resistant to trauma for reliving events. They can't see it in their head. It's like, do people who have had aphantasia daydream? Do they see things in their head, etc.? A memory, call it up, etc. So maybe it's a painful memory, but they can't relive it because they can't see it in their head, and they might have a better time. But it's an interesting situation. Some people see colours. They hear a word or they hear a thing, a sound, and they can see colours. This is something else in the head that people can't see imagery. We've got a current feature in our magazine on psychology and all the aberrations that people have. And aberration might be the wrong word. It's just a variation across the spectrum in so many different areas, and this is just one of them.
That's Tim Mendham from Australian Skeptics. That's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.